Hi, welcome back to the lecture series on Abstract Measure Theory with course code MTH701 and MMTE305. Today in this lecture we discuss some more properties of monotone functions. First of all, we define the divided difference function and average value function. So, divided difference function and average value function. Divided difference function and average value function. Okay, suppose we have a given integral function which is defined on closed and bounded interval. Let f be a function defined on closed and bounded interval, defined on closed and bounded interval. Okay, this is a given function. We extend f to take the value f of b. We extend f to this interval to a to b plus 1, where this f of x is equal to f of b. Its value is f of b, or on this if b is lesser equal to x, at x equal to f of b, because it is defined here, its value at b is f of b. But for the values for the x, for those values of x which lies between, which are greater than b and but less or equal to b plus 1, so its value is equal to b. It's constant on this interval, actually b to b plus 1. We extend our function f to this interval a to b plus 1 by defining f of x is f of b on this interval b to b plus 1. Now I will explain why we are extending this, because we want to define divided difference function and the average value function. That's why we extend our function to this interval a to b plus 1. So first of all, we define divided difference, and now we define divided difference function and the average value function. For 0 less than h less or equal to 1, 0 is a h is a positive number but less or equal to 1, define the divided difference function. Define the divided difference function. Define the divided difference function, which we denote by this notation, diff subscript h of f. Okay, this means the divided difference function. Okay, and average value function, and we define average value function. Average value function. The notation for this average value function is an average value function which is denoted by a v subscript h then f. Okay, avh of f. On this we define on this interval a to b by this divided difference of f is equal to, its value is equal to f of x plus h evaluated at x, its value is f of x plus h minus f of x divided by h. Now since this x is x lies in this interval, that means a less or equal to x, less or equal to b, but now we have here x plus h. H is a positive number, less or equal to 1, so therefore x plus h lies in the interval a to b plus 1. That's why we have extended this function over on this interval a to b plus 1, because here the value of this value of this x plus h lies in the interval a less or equal to a to b plus 1. Okay, because h is less or equal to 1 but greater than 0, and x is less or equal to b. So x plus h is less or equal to b plus 1. Okay, and the average value is, and the average value AVHF evaluated at x, it's equal to 1 over h. The integral x to x plus h, x to x plus h, okay, f of t dt. So these the definition is of divided difference function and average value function. Now we see very interesting property. We apply the change of variable formula, and we will see that now we verify that. Now we verify that. The integral we verify that the integral u to v divided difference of f, it's equal to average value at v, average value of f at v minus average value of f at u. So this we verify. Okay. Now we verify that. This one. Okay. So name it 1 here. So to verify 1, we take the right hand side. RHS of 1 is equal to AVH of f evaluated at v minus AV. I think I take it's left hand side. Okay, not the right hand side. Should take the. So we have this integral u to v f of t, sorry, it's divided difference, divided difference of f, this integral it's equal to integral u to v. What's divided difference of f? It's f of x plus h, or you can write it as t plus h also, not a problem. So I will write it as let me write it as t plus h. Okay, let me write it as t plus h, because we are integrating with respect to this x or t. You can take any variable here, minus f of t divided by h dt. That's equal to 1 over h. So let me write this as I. Okay, this implies our I is equal to integral u to v f of t plus h, okay, minus 1 over h integral u to v f of t. Okay, this is your dt. Okay, let me denote this by I1. This is equal to I1 minus I2, and name it second. Okay, so this I is equal to I1 minus I2, where I1 is equal to 1 over h integral u to v f of t plus h, and I2 is equal to 1 over h integral u to v f of t dt. So now we will see this. We'll try to simplify this integral I1. Okay. So now this I1, and name that expression as 2. Yes. So this is now integral I1. Now integral I1, which is equal to u to v f of t plus h, it's 1 over h dt. Okay, 1 over h dt. We replace this t plus h by t, or you will put t plus h. Put t plus h. I think I should write here. I should write here y plus h rather this t. Okay, because I need. Let me write here y plus h. This will not affect our value of the integral actually. So let me write here y. Let me write here y. Let me also write here y. Here it's y. This is integral. This is integral dy. Okay. Okay. Let me write here integral y plus h dy f of y dy. It's dy here. It's d. Okay. This is dy here. Okay. Sorry. It is a. It's here y, then it's here dy. Okay. So that clear. It's y plus h. Okay, it's y plus h. Now what we do, it's here it's y plus h. Okay, y plus h, and this is here dy, not dt. This is dy. So what I will do, I will put this y plus h equal to t. Y plus h equal to t. Put y plus h is equal to the variable t. Now what will happen to the limiters? Whenever y approaching to u, t approaches to u plus h. Whenever y approaching to v, t will approach to v plus h. You will see then this integral I1 is equal to 1 over h integral u plus h to v plus h f of t, and dy is same as dt. So let me substitute this value again in 2. Therefore from 2 we have this integral I, which is equal to I1 minus I2. What's our I1? So I1 is this integral 1 over h to u plus h to v plus h f of t dt. So it's 1 over h integral u plus h to v plus h f of t dt minus that I2, which is equal to 1 over h integral, it's u to v f of t dt. Okay, so this is it. Now I will try to add and subtract some things so that I will get the required formula. So it's here u plus h to v plus h. It's here u to v, but the sign is plus here. So can I do here? I can't write it as minus times this. Okay. V to v plus h. So let me write it as. Can I write it as minus times so that? Okay. So let me write it as. Let me subtract this number minus 1 over h integral v to v plus h f of t dt, and let me add this number also, 1 over h v to v plus h f of t dt. So no problem. And let me this one, let me write this this one. Then I have subtracted and added the same number. Then I write the term this one which this is here plus I can write it as minus times integral v plus I. I have changed the order of the limits of the integration, so it's actually plus, but this is now minus times because I have changed the order of the limits here. F of t dt, then I have this term which is minus, this is 1 divided by h, okay, 1 divided, then minus 1 divided by h integral u to v f of t dt. Okay, okay, you can see this I have done here. The I is equal to that difference, and then I have written here minus 1 over h v to v plus h f of t dt, and plus 1 over h v to v plus h f of t dt. Then I have write this one as minus 1 over h v plus h to u plus h f of t dt. Then this is the term here, minus 1 over h u to v f of t dt. Now I will club these minus terms together. Okay. This is equal to, so first I will take the positive term, which is equal to 1 over h v to v plus h, 1 over h v to v plus h, it's equal to 1 over h integral v to v plus h f of t dt. Then it's minus times the rest of the terms. So first of all I will write u to v, then I will write v to v plus h, it's equal to integral u to v f of t dt plus integral v to v plus h f of t dt plus integral v plus h to u plus h f of t dt. Okay, it's minus times these three terms, which is equal to 1 over h integral v to v plus h f of t dt, and this one you can add it's u to v, then v to v plus h, then v plus h to u plus h, it's equal to integral u to u plus h f of t dt, and this one it's equal to the average value of f evaluated at v minus average value of f evaluated at u. So that's our I, but I is the integral of divided difference, so which implies that integral u to v divided difference of f, it's equal to average value of f at v minus the average value of f at u. So that's the desired formula that we have derived. Okay, this formula we will use in our coming results. So remember this formula, integral of the divided difference u to v is equal to average value of f at v minus average value of f at u. So this is very important formula because we are using in our results. Okay, this formula is very important. Now next we have following a theorem. Next we have a following theorem which is for the increasing function. So let me write the statement first. Okay, what is the statement? Let f be an increasing function. Let f be an increasing function. Let f be an increasing function on the closed and bounded interval. On the closed and bounded interval, okay, which is AB. This is closed and bounded. That means A and B are, they are real numbers. They are not extended real numbers. It's a bounded closed interval. Then this f dash is integrable over AB. Then its derivative, okay. Then f dash is this f dash exists almost everywhere. This is by Lebesgue's theorem, which we have done in the previous theorem. So this exists almost everywhere. Now in this theorem we will show that this f dash is not only differentiable almost everywhere, its derivative is actually integrable. This f dash is integrable. This f dash is integrable. This f dash is integrable over the same interval, over this interval AB, and this holds integral a to b f dash is less or equal to f of b minus. This is actually some sort of a generalization of the fundamental theorem of calculus, where we are given that this f is differentiable. Then the integral is exactly equal to f of b minus f of a. Actually, that's a fundamental theorem of calculus. But here it is some sort of generalization. Given an increasing function f, this is always true actually. And in our coming lectures, we will see that when the converse is also true for the general Lebesgue integral. Okay, when this converse is also true. When we say integral a to b f dash is exactly equal to f of b minus f of a. In general, for increasing function, this strict inequality may hold. We will also give an example where this strict inequality hold. So for this example, we need to define the Cantor set, and then we need to define the Cantor-Lebesgue function. For the Cantor-Lebesgue function, this inequality is strict, and in that example, we will conclude that Cantor-Lebesgue function is not absolutely continuous. But that's always a bounded variation. Cantor-Lebesgue function is bounded variation, but not absolutely continuous. That we'll discuss later on. Okay. So first of all, we will see this. In general, for a monotone function f over closed and bounded interval ab, this is always true. This is always true. Integral a to b f dash is always less or equal to f of b minus f of a. So let's prove this theorem. Prove. Okay, again this we can extend this f. So this f is increasing since. So let me first write this extend f on a to b plus 1 by defining f of x equal to the f of b whenever b less or equal to x, less or equal to b plus 1. Since f is increasing over this interval a to b, therefore f must be increasing over the interval a to b plus 1, because it is taking the last value on this interval b to b plus 1. Okay, then this f is increasing. Then f is increasing on the interval a to b plus 1. F is increasing on this interval. So that means every increasing function is measurable, in fact. So therefore the divided difference functions are also measurable. Then f is increasing and therefore, and this is increasing, therefore measurable. Therefore measurable. It is increasing, therefore it is at most countable even in discontinuity. That means it is continuous almost everywhere over this interval also. So it must be measurable. Thus the divided difference that the divided difference functions, which are these functions. This is not a single function. They are because they depend upon f. They depend upon h actually. This is equal to f of x plus h minus f of x divided by h. They are also measurable because this is measurable, this is measurable. Difference of two measurable function is also measurable. Thus the divided difference functions are measurable for 0 less than h less or equal to 1. They depend upon h actually. If we vary our h, we will get the different divided. Suppose for h equal to 1, the divided difference function is evaluated at x. Its value is equal to f of x plus 1 minus f of x divided by 1. In case h is equal to 2, then this divided difference function, which is evaluated at x, the value of that function at x is equal to f of x plus 1 over 2 minus f of x divided by 1 over 2. So this is not a single function. It's actually a collection of. In fact, it's an uncountable class because this h varies over the interval 0 to 1, which is uncountable. Okay. So these divided difference functions, they are also measurable because f is measurable. Okay. So this is a measurable collection actually. Now by Lebesgue's theorem, which we have done in the previous theorem, by Lebesgue's theorem, this f is differentiable almost everywhere. F is differentiable almost everywhere on this interval, on open interval a to b. This is already done. So therefore the sequence, this one, divided difference sequence. Now we'll take h is equal to 1 over n. Now it's now countable class, okay? Because here we have taken h is equal to 1 over n. So this n is greater or equal to 1. So obviously this n lies in the interval n to this 1 to 0 to 1. Okay. This is 1 over n of f. N runs from 1 to infinity. Therefore, this is a sequence of measurable functions. Measurable functions, non-negative. In fact, it's non-negative sequence because f is monotonic increasing. So this divided difference is equal to f of x plus 1 over n minus f of x divided by 1 over n. F of x plus 1 over n is greater or equal to f of x because f is monotonic increasing. So it's a non-negative sequence of measurable functions. That converges, because whenever n is approaching to infinity, the limit of f of x plus 1 over n minus f of x divided by 1 over n is equal to f dash. That converges pointwise. The limit is always pointwise almost everywhere on this interval a to b to the function f dash to f dash. It's actually because of this reason. You can see this. You can see if you want to see the reason of this. Reason is that the divided difference of 1 over n of f at x pointwise, it's equal to f of x plus 1 over n minus f of x divided by 1 over n. So this limit is approaching to f dash whenever f dash exists at this point x, and this exists almost everywhere because f is differentiable almost everywhere, because whenever n is approaching to infinity, this will approach to 0. It's like f of x plus h minus f of x divided by h, where h is approaching to 0. This n is here approaching to infinity. So this is the reason, you can see. So that sequence of divided difference function, it's a non-negative sequence of measurable functions that converges pointwise almost everywhere to f dash, because f dash exists almost everywhere. Now we apply Fatow's lemma. According to Fatow's lemma, which you had done in the previous course, according to Fatow's lemma, we conclude the following. We have integral a to b limit inferior of this sequence which divided difference is less or equal to limit inferior of the integral a to b of divided difference 1 over n of f. But this is actually the limit of this exists. It's equal to f dash, so its integral a to b f dash is less or equal to limit inferior of this is here a to b, this is a to b divided difference. What's that? We can apply that formula which we have already derived in the equation number 2. What's that? Where we had derived that integral u to v divided difference of f is equal to average value at b minus average value at a. But that average value which this is equal to average here h is 1 over n, average value of f at b minus average value of f at a by 2. Okay, and that's equal to limit inferior. What's this average value? This one, this average value. What's the definition of average value? From the definition you can conclude that this average value at x is equal to 1 over h, x to x plus h. But here its average value at b, it's 1 over h, means here 1 over 1 by n, because h is here 1 divided by n. Okay, integral b to b plus h, h is 1 over n. Okay, then it's f of t dt minus average value, it is 1 over h, h is 1 over n, integral then it's at a means a to a plus h, h is 1 over n, f of t dt. Okay, so integral a to b f dash is less or equal to limit inferior and then limit inferior of this. Okay, now this one you can see this is always less or equal to f. This is f of t is equal to f of b here, and this one is so can I do here this is equal to here f of b. Okay, this is equal to, okay, let me write, this is equal to limit inferior, then it's n times integral b to b plus 1 over n, but the value of the function over this interval, over this range, is f of b dt, then minus n times integral a to a plus 1 over n f of t dt. Okay, now this one you can see this is equal to limit inferior of now what is this? It's what's the value? It's n times f of b into the integration of dt is t. Then we apply the limits b plus 1 my limit of the t, that its integral is t and the limit is b to b plus 1 over n. So it will be b plus 1 over n minus b, that's equal to 1 over n. Okay, then I will apply this minus limit inferior minus time, this will be minus time the limit superior. Okay, minus times limit superior of integral a to a plus 1 over n f of t dt. These two will go, this is just f of b, but this one, now this is again less or equal to, okay, this is exactly equal to f of b. Okay, let me write here exactly equal to first, because it will create confusion. Okay, this is equal to f of b minus limit inferior of sorry, it's limit superior, not limit inferior now, it's now limit superior. Okay, limit superior of the integral a to a plus 1 over n f of t dt. Now this f of t, it's greater or equal to f of a, because on this range a is less or equal to t is less or equal to a plus 1 over n, so that means f of t must be greater or equal to f of a, which means that minus f of t minus times this will be less or equal to minus times f of a, because the sign is here minus, so it is less or equal to f of b minus limit superior integral a to a plus 1 over n just f of a dt. Now here it's actually here n times, okay, n times, okay, it's n times here, n times this, and this one now it's equal to f of b minus limit superior into n. Then you see this integration, what's this integration, it's equal to f of a times 1 over n, f of a times 1 over n, because the integration is equal to t and the limits are a to a plus 1 over n, so it must be 1 divided by n, that's equal to f of b minus f of b. So thus integral a to b f dash is less or equal to f of b minus f of d. And the more general form for this is it's actually the more tighter form of this is actually the tighter form of the inequality is you can see it's the tighter form of the inequality is the following: a to b f dash is less or equal to supremum of f of x, where x runs over the interval a to b, minus infimum of f of x, where x runs over the interval a to b. So this is the tighter form of this inequality, because this integral is actually independent of the endpoints, you can see. So because you are always integrating over this interval a to b, but you are taking the values of the function in the open interval a to b, so that means it is actually independent of these endpoints. Okay, it's independent of the endpoints. And you can apply this for any extension also, because you are extending the function f over the interval a to b plus 1. You can do any other extension over the interval a to b plus 1 over 2, or over the interval a to b plus 2. So this inequality holds for over any extension actually also, over any extension. So if I will choose this supremum rather than this f of b, this will work. And here if I choose the infimum instead of f of a, you can see it here actually. Let me go back first, because here actually this one where you had defined the function f of b, So here we have taken f of x equal to f of b over this interval. If I choose f of b instead of f of b, if I choose the supremum of f of x over the interval a to b, this will still work. This will still work. Okay. So and here if I write here the infimum of f of t over this interval, this again will work. Okay. That's why the more tighter form and in case our function is continuous at these endpoints, then this infimum will be equal to f of a and this supremum will be equal to f of b, because the function is monotonic and increasing. Then we get this inequality actually. Okay, so this is more tighter form, because f of b may not be the supremum of f of x over the interval a to b. So, but it's always less or equal to f of b over this interval. So that's true. This is the more tighter form actually. The supremum is always less or equal to f of b. Okay, and the infimum is always greater or equal to f of b actually. So this is the tighter form actually of the inequality. Of our inequality, this is tighter form. So next we discuss the uniform integrability first. When we say the class of integrable functions is uniformly integrable, that's our next topic actually. Okay, that's our next uniform integrability. Uniform integrability. So here we only state our results. We will not prove those results because actually this is not in our syllabus, uniform integral, but we are going to use these results which we derive later on. So let me state first the lemma, which actually is very simple, and you can see its proof in the book written by H.L. Royden at page number 92, which is very simple. So let me state this lemma first. Then we will define this uniform integrability. Let E be a set of finite measure. Let E, which is actually very simple, let E be a set of finite measure and delta is a positive number. Then we can express this E as a finite disjoint union of finite collection of sets. Then this E can be expressed as a finite disjoint union, union of sets, each of which has measure less than delta, each of which has measure less than delta. And this is trivial for the interval. Suppose we have interval 1 to 2, we can choose that partition so that the Lebesgue measure of each interval, sub-interval, is less than delta, and we can express this A as a finite disjoint union of members, finite disjoint union of sets, such that the Lebesgue measure of each set is less than delta. But you have to prove it in more general. You have given any set of finite measure. It may not be the subset of the real line R, but here okay, it's a subset of, let E be subset of R. Okay, so this is true for the real line. Okay, it's a Lebesgue measurable subset. It's Lebesgue measure here. Then we can express this A as a finite disjoint union of sets such that each set has a measure less than delta. So if E is interval, then there is nothing to prove. Here you will see the lemma, we are using the partition of the interval. Okay, you can see the proof in the elements if you are interested. So next we have a proposition. I will leave the proof of this proposition, which is again very simple. You can see it on this elephants, not on elephants, on the book written by H.L. Dryden, the real analysis. The title of the book is Real Analysis. Okay, the proposition is let f be a measurable function. Let f be a measurable function. Let f be a measurable function on E. Let f be a measurable function on E. If f is integrable, this is very important. If f is integrable, you will use this property in future. If f is integrable, over E, if f is integrable over E, then for each epsilon positive, there is a delta positive. There is a delta positive for which this holds. If A subset of E is measurable and its Lebesgue measure is less than delta, so it's these results are only for the Lebesgue measurable functions. If Lebesgue measure of this set is less than delta, this should imply the integral of the mod of f over this set A having Lebesgue measure less than delta. This integral should be less than epsilon. So if f is an integrable function, if f is a measurable function, then this f is integrable over E. If f is integral over E, then for each epsilon positive I can find delta positive with this property. For any subset A of E which is measurable having measure less than delta, then integral over the set A must be less than epsilon. Now let's define the uniformly integrable class. Okay. Definition. Okay. Definition. A family F of measurable functions is said to be uniformly integrable over A. Of measurable functions over E, okay, over E is said to be uniformly integrable over E, provided for each epsilon positive, there should exist delta positive, such that if A subset of E and Lebesgue measure of A less than delta is measurable, and its Lebesgue measure is less than delta, this should imply integral over A of the mod of f is less than epsilon. This should happen for each f belongs to that class f. So this if delta exists uniformly for each f actually. If this is true for each f, this delta is uniform for each f. If for each epsilon positive there is delta positive such that this holds for each f in f, then we can say this collection f is the collection of uniformly integrable functions. So here is an example of uniformly integrable collection. You can easily verify that. Again, you can see that H.L. Dryden for this. Let G be a non-negative integrable function. Let G be you have to apply the previous proposition, G be a non-negative integrable function, G be a non-negative integrable function over E, then we define this collection F, which is equal to F such that F is measurable and mod of F is less or equal to G on this set E is uniformly integrable. It's very simple. You have applied the previous lemma. Is uniformly, you apply by previous proposition, okay, by previous proposition. It is the application of previous proposition actually, okay. And in fact we have a following exercise. Show that any finite collection of integrable functions over E, show that any finite collection of integrable functions over some set E over E is uniformly integrable over E. It's again simple. You have to choose the minimum delta, okay, because it's a finite collection, so we have finitely many deltas actually by proposition, by apply. So hint is here, apply the proposition, apply previous proposition, apply previous proposition, okay. And next we have Vitalik convergence theorem. Again we will not prove this theorem. Vitaly will only use this theorem, Vitaly convergence theorem. Its statement is, let E be a set of finite measure, let E be a set of finite measure, suppose the sequence Fn is uniformly integrable, suppose this sequence is uniformly integrable over E. Now if this Fn it converges to F almost everywhere on E, then this should imply then F is integrable. Then you have to show that this F is integrable. Then the conclusion is this F is integrable, and we can pass the limit through integration, okay. Then F is integrable, and this integral and the limit of the integral of Fn is equal to integral of limit of Fn. This is not defined because limit of Fn is integrable. Fn converges to F and F is integrable, okay. So this integral is valid. It is over E, in fact, over the set E. So limit of the integral is equal to integral of limit, which is equal to integral of F actually, because limit of Fn is equal to F. So again this will not prove this theorem here. So we'll apply this theorem in our coming results actually. So I conclude this lecture here. So in the next lecture we'll discuss certain properties of these results, okay, and we will also see that we'll also discuss the indefinite integral, and we'll see that the indefinite integral is always absolutely continuous function. So these are some properties of absolutely continuous function. In fact, we'll also see that that in the theorem where we have seen that this is less or equal to when this inequality will be hold. Okay, we will see this. Here we have proved this result. Where it is this one. Okay, not this. It is it's here. So we'll see that if f is absolutely continuous function and it's also monotonic increasing, then this integral a to b f is always lesser. In fact, it's actually if and only if condition. We'll see that for a monotone function, the equality here, the equality holds if and only if f is absolutely continuous. And where we will see that the function which is constructed by Cantor and Lebesgue, which we call the Cantor-Lebesgue function, that function is not absolutely continuous, because we will see that that function is monotonic increasing, but for that function here this strict inequality holds. So it means that the function cannot be absolutely continuous, because for absolutely continuous